Mm-hmm.
I don't know what's going to make it.
Well, the issue is those are not necessarily triaxial. The question is if you have triaxial orbits, you have a lot more things that are on nearly radial orbits that eventually become these. And so it can lead to an enhancement of high eccentricity objects in the 4-day period range.
One is going to be, well, one is going to quantify the energy.
No, these things, yeah. I'm sorry? It included the white dwarf confusion noise, and it was for all the channels, yes, both polarizations.
Okay, one last question.
What are
We'll
the
talk afterwards.
periapsis distances like in terms of the mass of the central black hole? That is, are these coming by at 6 am or at 6,000 am? I'm trying to get
Yeah, and I don't remember. I don't remember. But we excluded anything that was within that would have been captured.
Right. So anything inside 6 am you excluded.
Yeah, that's right.
So is the median a little outside there, or is it like?
I do not remember. Yeah. Mm-hmm. Yeah.
Okay, let's find out if we want to
Oh, yes, I probably do. All right, let's. But you don't want to hear my comments?
It might get interesting halfway through a talk, but I don't think we're going to. Okay.
Hold on. I'm getting both cards. Sorry.
I'm actually stealing something else. I've got your PDA as well. Very good. Okay. There we go. Right. Okay. Emanuele is going to talk about waveform models and time estimations.
Okay. I will really approach the problem from the high mass end, and in fact I will start talking about the astrophysics of supermassive black hole binaries, arguing that maybe some of these supermassive black hole binaries have a very low mass ratio. So I will tell you something about the formation of supermassive black hole binaries and also on mixed binaries where you have one supermassive black hole and an intermediate mass black hole. I will tell you something about my present astrophysical understanding of the masses, the mass ratios, the spins, and the eccentricity of the systems. And I will give you some preliminary calculations that I made for the signal-to-noise ratio for in spiral waves from IMRIs. And I will compare these calculations to calculations that I did in the past with Alessandra Buonanno and Cliff Will for the signal-to-noise ratio of supermassive black hole binaries. And then I will try to tell you something about the physics we can learn from these systems. So I will tell you something about what we can learn about the supermassive black hole or IMRI merger history. I will tell you how we can use these systems to test general relativity, really to test post-Newtonian expansions of general relativity, and possibly on how you can use in spiral waves to place bounds on alternative theories. In particular, when we use these systems, we can place bounds on things like the graviton mass, loosely speaking, meaning deviations in the dispersion relation from the dispersion relation you will have if the speed of gravity were equal to the speed of light. Also, in the end, I will make some remarks on how I think we should improve theoretical waveforms to make all of the predictions that I will give you more firm. So I will tell you something about what happens if we include higher order post-Newtonian terms, how this is going to change the estimates. I will try to argue that IMRIs, meaning systems where you have a supermassive black hole on mass of order 10 to the 6, and another black hole which can be on mass 10 to the 4, 10 to the 3, or 10 to the 2, are systems which are, in a sense, in a buffer region between the different approximations that we usually use to compute waveforms. So So the post-Newtonian approximation doesn't really work well in that regime. And the Joukowsky approach doesn't work well either because the mass ratio is not really small. Then I will tell you something about how numerical relativity can be useful and if it can be useful in this context, in the sense that we want to match the inspiral and during down waveform, and maybe we can learn something from that. And also I will tell you something about measuring the spins using these systems and what happens if you have higher harmonics in the signal. These higher harmonics can come from post-Newtonian amplitude corrections. Usually when we compute the waveforms, we use what is called the restricted post-Newtonian approximation, which means that we take the leading order term in the amplitude and we include corrections in the phase. But if we want to include corrections in the amplitude as well, that is going to show up in the appearance of additional harmonics, which can actually be useful because then you can look at larger mass systems. Or these higher harmonics can come from a physical eccentricity in the very last year of inspiral, and I will tell you something about what this could imply. Okay, I will start sketching what we know about supermassive black hole binary formation event rates. Well, you know about the standard scenario. There are lots of astrophysicists in the audience, so I'm not going into the details here because you know this very well. You start with two black holes which are widely separated. They sink to the center by dynamical friction. Then they get closer because of interactions with gas or gravitational slingshots. And eventually gravitational radiation takes over. Eccentric binaries, there's a bias here towards eccentric binaries in the sense that the merger timescale is shorter for eccentric binaries. And then you can have something which is called the gravitational wave recoil that comes from the fact that in the very last phases you radiate linear momentum besides angular momentum. Now, the point is, this is a very nice scenario. Everybody more or less agrees about this scenario, but then what do you start with? And if you start with population 3 stars, which is more or less the standard scenario that was proposed by Madao and Rees originally, what you get is initial seed black holes which have a mass of around 100 solar masses because they come from the collapse of these population 3 stars which have a mass in the range 30 to 300 solar masses. So you have relatively small seeds, and these seeds start merging, they form larger mass black holes, and eventually you have a signal which comes mostly from this black line here, because remember that to have a LISA interesting binary, you need a mass in this mass range. So most of the events you will have in a mass range that peaks, in a redshift range that peaks around 5. There are also alternative scenarios that we can probe with LISA, where you start from the direct collapse of low angular momentum material in progalactic disks. So you don't go through star formation. These systems can form at larger redshift, and they will have seed black holes of mass of order 10 to the 5. And as you merge these seed black holes will have a larger mass, and they will cause a much larger background of gravitational waves. And in fact, the rates strongly depend on what you assume. So this is a table that I put together for the proceedings of the gravitational wave data analysis workshop, where I collected rates from many different papers in the literature. And you can see that for supermassive black holes, these rates range all the way from 0.1 to a background which could be stochastic or resolvable. Actually, these authors, in a later revision of their paper, claim that the background is resolvable. So the point is, we don't know what is going to happen. We could have a very large background of supermassive black holes, or if you look at most of the predictions, what is most likely is that we will have around 10 black holes, with most of the events occurring in this redshift range. Besides this scenario, there is the scenario for the formation of IMRIs that Cole was mentioning the other day, where you start with a young stellar cluster, you form an intermediate mass black hole. This intermediate mass black hole falls into the central massive black hole. The young stellar cluster is totally stripped. In the end, you have this single intermediate mass black hole that falls in. And there have been some papers over the last year about this, guesstimating the rates. And the guesstimates are between a few and perhaps 100 IMRIs per year. And here we're talking about systems where the mass ratio can be significant. Now, even if you don't take systems where the mass ratio is like 1,000 to 1, the distribution of masses and mass ratios which are predicted in these different scenarios are such that the mass ratio is really an important factor. So here on the left, I'm showing a prediction from the scenario by Marta Volontari and others, where you start from population 3 remnants. And you can see that in the interesting redshift range, the mass ratio is typically around 0.1. And if you look at the other scenario, where you start from the collapse of protogalactic disks, look at the points, the mass ratio goes down to something like 10 to the minus 2. So how do we want to model these systems? Are they IMRIs or what? Well, spin is a very major factor, and the reason is that over the merger history, the spin of the black holes can grow through accretion or mergers, and accretion is definitely the dominant mechanism. What happens is that if you assume that accretion is efficient, so you have a thin disk, roughly 70% of the total of the black hole population is nearly maximally rotating. But even if you make more conservative assumptions on the efficiency of accretion, around 80% of the black holes have spin larger than 0.8. So we really want to include the spins, and we want to be able to measure them. Finally, eccentricity. I will take an agnostic point of view here, and I will just mention some mechanisms which have been proposed to have significant eccentricity, perhaps all the way to the frequency region where the signal enters the Lisa band. These simulations are M-body simulations. They were mentioned in the paper by Rainer Spurzem, and here I show a plot taken from their paper where you can see that there's a significant increase in eccentricity. This is 1 minus C. So as they increase the resolution of their simulations, they clearly see a trend of increasing eccentricity. And the question is this eccentricity still going to be there when the signal enters the Lisa band? Cole Miller put some notes online where he argues that this eccentricity should be washed away by the time the signal enters the Lisa band, but this is not totally clear, and we have to take it into account. There are also mechanisms where the binary interacts with a circumbinary disk, and this can possibly excite the eccentricity to something like 0.1 if you consider the typical mass ratios 1 year before merger. So just keep in mind that there's a possibility that what we want to observe is eccentric. Now, this is a very useful plot that I took from a paper by John Baker and John Centrella, where you can see the kind of systems we can observe with Lisa, the marks on these lines, this is the signal, the noise curve of Lisa, and these lines show the characteristic amplitude of the waves for different systems, and the optimal systems for the observation with Lisa are black holes where the typical mass is around 10 to the 6. If we have larger mass, we get out of the Lisa band. Most people think that you cannot really trust the Lisa noise below this dotted line. So this is the kind of system that we want to observe. Which signal-to-noise ratio are we going to have for these systems? This is a calculation that I made where I show you the signal-to-noise ratio, which is given by this quantity. H is the gravitational wave amplitude. You divide it by the Lisa noise, and you take this integral. Now, the signal-to-noise scales with these powers of the mass and eta, where eta is the so-called symmetric mass ratio. This means that small mass ratio binaries, so IMRIs, will have typically a smaller mass ratio by a factor which is roughly the square root of the mass ratio. And larger mass binaries will typically have larger signal-to-noise ratio. Then the shape of this curve depends on the Lisa noise. And this is the actual calculation. Here I truncated the lines when you can observe less than the last year of inspiral. So these lines end for systems for which you can see less than the last year of inspiral, assuming that you can extrapolate the Lisa noise all the way down to 10 to the minus 5. And then I said, what happens if you cannot trust the noise below 10 to the minus 4? And this is where I put the dots. So for systems to the left of the dots, you can observe the last year of inspiral, even if Lisa is blind below 10 to the minus 4 hertz. The solid lines have a mass rate. Here I consider systems with the typical mass ratio for supermassive black holes. And I took different values of the cosmological redshift. So I start from 0.5 and I go all the way down to z equal 10. And these are IMRIs. So for IMRIs, typically you have a signal-to-noise ratio of the order of 100 or so. which is roughly at least 3 times larger than the signal-to-noise ratio that Kurtz and Lior Barak were considering in their paper on IMRIs. So I will show you later that this reflects in a better parameter estimation compared with IMRIs. Fine. So how do we do parameter estimation? I will just very quickly go through this. You have a gravitational wave waveform, and this waveform will depend on some parameters, which in the case of the in-spiral are the masses, spins, sky location, orbital orientation of the source. For high signal-to-noise ratio, the errors have a Gaussian distribution, where the Gaussian distribution is determined by something which is called the Fisher matrix. And you can compute this Fisher matrix given a model for your signal. You invert the Fisher matrix, and the diagonal elements of the inverse of the Fisher matrix, which is called the correlation matrix, give you the errors. Right. Now, since we take into account the motion of LISA around the sun, what we want, what we are most interested in are the errors on things like the masses, spins, the so-called intrinsic properties of the binary, to use the language that Kurt was using the other day. So what we do is we take many binaries, 10 to the 4 binaries in the simulations that I'm going to show. We place them in random positions in the sky and with random positions of the orbital angular momentum. And for each of these binaries, we compute the error in the estimation of the masses, in the estimation of the distances, and so on. And then I will show you a histogram of these errors for the different parameters. Now, this is the waveform that we use to do the calculation. Let me spend some more time before I show you the histograms to tell you what we can do using this waveform. Now, this waveform, the crucial element in the determination of the parameters is the phasing of the waves. And this phasing has a leading order term, which depends only on the chirp mass. So we expect the chirp mass to be the parameter that we can measure best. Then there are corrections, which are these black terms that are corrections in standard general relativity. They are post-Newtonian corrections, and they depend also on the mass ratio, if you like, eta. So if you take into account those, you can also measure the mass ratio, or if you like, the mass of the other member of the binary. And then you can assume that general relativity is not all, so perhaps there are extra terms. For example, I will show you later what happens if you include this blue term, which would be there if you had a mass of the graviton that modifies the dispersion relation. In this case, the phasing of the waves is modified by something that depends on the mass of the graviton, lambda g is the graviton Compton wavelength, and on the distance to the binary. And if you assume that term is 0, and you look at deviations from 0, you can set bounds on the mass of the graviton for a given distance and binary mass. Right. Now, these are the histograms that I was talking about. Ignore the lines in color. These are for supermassive black holes. And you can see that the typical measurement errors for supermassive black hole binaries are really small. This is the measurement error on the chirp mass. This is the measurement error on the reduced mass. So these are typically 10 to the minus 5 or 10 to the minus 4. And then you can see the black line is when you use a single detector, and the red lines are when you use both detectors. Here you see the errors on the distance, and these are typically between, say, of order of 1%. They can be as large as 10%. These are errors on the angular resolution. So these tell you how accurately you can locate the source in the sky. And that is typically, this number looks very small because it's in steradians, but it's actually something like 1 squared degree. Now, this analysis that we made only included spins in the aligned case. Recently, this has been updated by Ryan Lang and Scott Hughes. So here they take a binary of 10 to the 6 plus 3 times 10 to the 5 solar masses, and they show that if you include spin precession, the estimates that are shown you get even better by about 1 order of magnitude on the masses. For the angular resolution and the distance, things don't change much, but you can also measure the spins. And you can measure the spins depending on what you assume for the background. They assume random spins or maybe spins of different magnitudes. The number that you get for the error on the spins is typically of order 10 to the minus 2, 1%, say. Now, these are the new calculations that I made when I was asked to give this talk, I thought, okay, let's see what happens if I push down my calculations in mass ratio, and how accurately can I determine parameters for IMRIs. So the solid line is the curve that I've shown you before for a supermassive black hole at 3 gigaparsecs. And this is the signal-to-noise ratio distribution that I get for binaries randomly distributed in the sky for an IMRI. So it's roughly around 100 or so. And when I look at the angular resolution degrades roughly by an order of magnitude. So I cannot really locate the source in the sky. But if I look at the distance determination, the decrease in accuracy is not so bad. Perhaps I can determine the distance to an IMRI for a cosmological redshift of order 0.5 or 1 within maybe 10% or so. And what I was really surprised to find is that the masses are determined as accurately as they are for supermassive black holes. And the way I understand this is that this is basically dependent only on the phasing of the waves, not so much on the amplitudes. And even if you have a lower mass ratio, you can still determine these numbers very accurately. I will skip this because this is, well, if you're interested, I can tell you something about how you can do cosmology, but this is mostly for supermassive black holes, so you don't want to hear about it. I will tell you instead something about how you can test post-Newtonian theory using in-spiral waves. Now, this is an idea that was tested by Arun, Balayer, Kusala, and Satya in 2 papers. So I'm showing results from both papers. In the first paper, they made a first rough analysis of what you can do, and in the second paper, they improved this analysis. The idea is the following. You have seen this very ugly expression for the phasing of the waves. Now, this expression contains certain powers of the orbital frequency multiplied by some factors. Now you can think, okay, I don't want to think of these factors as functions of the masses. I will keep them as free parameters. And these free parameters can be consistent with general relativity if their numerical values are consistent with the predictions of post-Newtonian theory for their analytic expressions as a function of the masses. So I take them as independent, and I carry out the Fisher matrix analysis that I've shown you before for the parameters psi. And then I assume a certain mass. In this case, for example, they assume a mass which is 10 to the 5.1, which corresponds to this point here. And they say, let's look at the regions in the parameter space of the masses where I have a certain measurement error delta psi on the various parameters psi. If GR is the correct theory, all these bands or weird-shaped regions in the parameter space should meet at the correct value of the masses predicted by general relativity. So it turns out that with LISA, for a binary distance of around 1 gigaparsec, this test works pretty well. And the more turns in the phasing you measure, the stronger the test you have. So this is, in some way, a strong field test of general relativity. Now, you can improve the analysis because actually you only have 2 free parameters. So you can say, okay, I can take the first 2 parameters to be known and check consistency of the others. And this is what they do in these other plots. Now, there's another idea that we explored with Alessandra and Cliff, which is, like I told you before, let's assume that the graviton has a mass. We don't have a consistent theory for this, but phenomenologically, we can assume that the only effect is to modify the dispersion relation, hence the phasing of the waves. Now, how well can we do to set bounds on the mass of the graviton in this way from purely gravitational wave observations? Well, we can do pretty well. In fact, you can see here, ignore the red line, just look at the black line. This is the bound you can set on the graviton-Compton wavelength if you assume that you can trust the LISA noise down to 10 to the minus 5 or down to 10 to the minus 4. Typically, the bound is of order 10 to the 16 kilometers. This is a number that you have to compare. First of all, this is a dynamical bound because it comes from the observation of dynamical gravity. And you want to compare this, for example, with solar system bounds, which are of the order of 10 to the 12, so 4 orders of magnitude worse. there are also some controversial bounds from the observation of bound galaxy clusters, but these bounds are very suspicious because there is no theory consistent with a massive graviton that explains cosmological observations. And there are also other ideas that have been tested by people in this room, Sam Finn and Pat Sutton, Kirk Cutler, Hiscock and Larson. There is also an idea that involves eccentric binaries that has been explored by Ian Jones, but I don't have the time to mention this. My last slide is about how we can do better. So one thing that we should take into account is the possibility that supermassive black hole binaries, or especially IMRIs, are going to be eccentric. And something that I'm exploring right now is what does this mean in terms of signal-to-noise ratio, and how does this change the data analysis that we want to carry out. Now, for eccentric binaries, this is a very preliminary plot in which we used a formalism that was developed some years ago by Moreno Garrido and others, which is based essentially on the Peters and Matthews formalism. And what I show you here is, okay, I take the primary to have a mass of 10 to the 6 solar masses, and the secondary as different masses that range from 10 to the 6 to 10 to the 2. So they span all the range from supermassive black holes to IMRIs, if you like. Now, if I assume that the eccentricity one year before merger is around 0.3, the n equal 3 harmonic has a signal-to-noise ratio that becomes comparable to n equal 2 for an IMRI. This is no surprise. I mean, this is something that people that study IMRIs see all the time. But if we want to study supermassive black hole systems in which one of the two systems is actually an intermediate mass black hole or has a mass significantly smaller than the other, this could have an impact. There are also other ways that you can get high-order amplitude corrections. Well, that you can get extra harmonics in the signal. And one of these is if you include higher-order amplitude corrections in the waveform. And this has been studied by Alicia Sintes and Vecchio, by Ron Hellings, and more recently by Vandenbroek in the context of LIGO. I don't have much time to talk about this. And then I will show you a table that clearly shows that the calculations that I've shown you so far are not so good. Okay? And the reason is that, okay, I'm done. The reason is that I'm using the post-Newtonian approximation, and when I go down in mass ratio, if I look at an IMRI, the number of cycles that are contributed by high post-Newtonian orders is of order hundreds to be compared with some thousands, maybe 20,000. So this is not small if you want to do parameter extraction. I will skip this part, and I will get to a summary. Well, you can read it, and if you have questions, we can talk about it later. Sorry for running out of time, but I always do that. Yes. Well, you can ask Kurt and Lior. For IMRIs, they typically get numbers for the masses which are of order 10 to the minus 4 in the accuracy, assuming a signal-to-noise ratio of about 30. So what the system that I've shown you right now was an IMRI with a signal-to-noise ratio around 100, then I got an accuracy of order 10 to the minus 5, which is consistent on the masses. But I'm not including many effects that they do include, like eccentricity, spin precession, you know, well, you don't include the spin of the small guy, which is very important for IMRIs, but let's say they are consistent with what they get for IMRIs. The trend is consistent.
I think a lot of people aren't really convinced that population 3 is I think there are a lot of other ways to build up the perhaps something.
This is the discovery space of LISA. We just don't know. We can't see to very large redshift by electromagnetic observations, and we should definitely use something like gravitational waves to understand which kind of scenario is correct. Okay.